And again, we'd like to welcome Trent Ford. Dr. Trent Ford has been the Illinois State Climatologist since 2019. And I think that's when I actually met Trent, was at the Illinois Specialty Growers Conference, and asked him if he could come and join us. And we were planning on that last year. He and his team provide online information through traditional and social media, and by speaking to interested groups across the state. In addition to his role in education and climate outreach, Ford also conducts research on the climate system and extreme climate events like drought and heat waves. He monitors current conditions and studies climate change. Trent is a native to Roanoke, Illinois. He earned his bachelor's degree in geography from Illinois State University before completing his master's and PhD at Texas A&M University. Before joining the Illinois State Water Survey, Trent was an assistant professor in the Department of Geography and Environmental Resources at Southern Illinois in Carbondale. Welcome today, Trent. We appreciate you coming out and giving us some information about our Illinois climate and how it's changing.
Yeah, well, thank you for having me. I'm going to set, I always like to use the clock on my phone to set a timer so I don't, so I know how long I've jabbered for here. So yeah, thank you for inviting me to come speak today. So as Chris mentioned, I'm the Illinois State Climatologist based at the State Water Survey in Champaign at on campus of the U of I. And I've been in that role for about 1.5 years now. And today I'm going to talk a little bit about our climate in general, why we have the climate that we do in Illinois, and then how and why it's changing, or it has been changing over the last 100 years or so. So when I talk about the climate, often, folks will think about climate as just the atmosphere, how much it rains, what the air temperature is, if we get hail or snow or anything like that. But in fact, the climate system, the weather is really just part of the climate system. This is really, this somewhat complicated schematic here is showing all parts of the climate system, which includes the biosphere, our plants and vegetation on the surface, the soil, the lithosphere below, all of the human influences, which is what we'll talk about when we talk about climate change, all the water, hydrosphere, the cryosphere, the frozen water parts, and then inputs from the suns, and then everything in the atmosphere. So, the climate system is really complex, and the atmosphere influences what's going on here at the surface and what we do, but also the things that we do and the things that are going on here on the land and below the surface influence the atmosphere as well. And so when we talk about climate change, climate change is typically defined by changes in temperature and precipitation, which is kind of how I'm going to frame it today. But in fact, climate change goes a lot farther than that, certainly with its impacts. And so that's a bit of what we'll talk about today. Okay, so kind of starting from the global view here, all of the energy that fuels our weather and that we can define our climate by initially comes from the sun. Okay, so there's the Earth's energy balance, or the Earth's energy budget. And really what it boils down to, the reason that we have energy, or the reason that we have weather, is that we have different amounts of energy that are coming in and affecting different places on Earth. And I'll describe that in a little bit here. What the schematic is showing you here is just kind of a simplified version of Earth's energy budget. So we get an amount from the sun. Most of that is absorbed by the surface. Some of it is absorbed by the atmosphere. Some of it goes right back into space. But the amount that's absorbed by the surface, a lot of that is re-radiated. So it's absorbed by the surface of the sun's energy, and then it's re-radiated, but it's re-radiated as a different type of energy, long wave radiation, which is we feel as heat. And some of that stays here on the Earth. And that's actually what we'll talk about here, this greenhouse effect, in just a little bit when we talk about climate change, but a lot of it goes right back into space. And in general, when we think about long time scales, the billions of years that Earth has been around, our Earth's energy is generally budgeted or balanced. How much energy comes in equals how much energy goes out. However, there are different amounts of energy that hit.
I don't know how to get the Volume up.
in different places,
The volume.
times of the year. And so what I'm showing you here is the amount of sunlight, essentially the amount of energy that we're getting
This is
from the
all
sun
louder I'm getting.
times at different places on Earth at different times of the year. So we have where we are right now, which is very close to the spring equinox. And on the flip side, in September, it'll be the autumn equinox. Now, the awesome thing about the equinox, and the reason the kind of base word of equinox is that there's 12 hours of sunlight all across the Earth. So whether you're at in Greenland, in Antarctica, or right here along the equator, or here in central and south central Illinois, you get 12 hours of sunlight on the spring equinox. Now we're moving from the spring equinox to the summer solstice, where the northern hemisphere where we are is tilted towards the sun. And so at that time, we're getting more energy overall, more direct energy, which means that more energy equals warmer overall temperatures. And then once we hit the summer solstice, the amount of energy we get in our day length, not to remind you all, but the day length begins to decrease after June 21st. And that's when we get to the flip side of that, which is the December solstice, where we're tilted the most, the farthest away from the sun, getting the least amount of energy. Now, at the same, this is why we have seasons. Why spring and fall tend to be the transition seasons, summer tends to be the warmest, and winter the coldest. And no amount of climate change that's induced by humans that we'll talk about in a little bit is changing that seasonality. At least winter is coldest, summer is warmest. At the same time, though, when you average that over the entire year, you get certain places on Earth that get more energy than others. Namely, if you think about the globe here, this area right around the equator, plus or minus about 20 to 30 degrees north and south latitude, this area gets the most energy over the course of the year. They have seasons too, although because the amount of energy along the equator between winter and summer doesn't vary nearly as much as it does here, it's pretty much warm all year round, which is why you can take a cruise, not right now, but hopefully soon you can take a cruise to the Bahamas in January and it will likely be pretty warm. And so in general, this area here along the equator, because it receives a good amount of energy over the entire year, they actually have a net energy surplus, which means they're gaining more energy from the sun than they're giving off, okay? And in contrast, as we get north of about 30 degrees north latitude, which is about Atlanta, Georgia's latitude, and south of 30 degrees south latitude, these areas, including where we live here, they get a decent amount of energy, but because of that winter season, we give off more energy than we get, which means that overall we have a net energy deficit. Now, if this were to continue infinitely, this area were to gain and gain and gain energy, and up here we'd lose and lose and lose energy, it would be unbearably warm here and unbearably cold here. But in fact, because nature likes things balanced, this inherent energy imbalance is attempted to equalize. And so what the mechanism that generates our weather is simply the air moving from around the equator, not just the air, but the ocean water as well, moving from the warmer equator to the cooler northern and far southern latitudes to try to equalize that energy imbalance, because energy imbalance drives a pressure imbalance. So it physically forces that air to move. And then we get cold air interacting with warm air, we get fronts, we get low pressure systems, we get high pressure systems, and that gives us our weather. So as I am teaching my students, I tell them, if we, hypothetically, if we were to have the same amount of energy over all of the Earth all the time, there would be no reason for that air to move. We wouldn't necessarily have weather. So that's what actually drives our weather here. So here in the mid latitudes where we are in Illinois, we get a lot of different types of weather. We have one of the most diverse climates, despite the lack of mountains or topography of any way. We have a pretty diverse climate here. Our summers are hot and humid, our winters are cold and sometimes snowy, and the spring and fall, it's kind of a mixed bag of what it brings. And this is kind of the result of that movement of how the air and conversely the oceans move energy from the equator to the poles. This here is showing the mid latitudes here in Europe. Of course, we're over here in North America. But the reason that this air moves from from south to north across the northern hemisphere, we get the westerlies, which is generally why the wind tends to blow from west to east. Storm systems tend to come from west to east because that's the predominant wind direction because of the combination of energy and air trying to get from the equator up north to the poles, and combined with the fact that the Earth spins, it creates those westerlies. So, as the air attempts to equalize that energy imbalance, weather is generated. So, thinking more about the specific types of climates we have here in the United States, this is what I'm showing, that the most traditionally used climate classification is the Copen, now the updated Copen Geiger climate classification. So most of the state of Illinois is here in this green, which is a warm, temperate, fully humid, hot summer, meaning that we do get seasonality. Our winters are cold, our summers are hot. It's generally humid the year round, so fully humid. There's not necessarily a very rainy season and a dry season as we get in some of our monsoonal climates, like here in Arizona, for example. And there's quite a large temperature difference between summer and winter. This line here that can maybe roughly be Interstate 72, that the only differentiation between the northern part of the state and the southern is really in the winter. We get more snow in north central and northern Illinois than they do in south central and southern Illinois in the winters. But if anybody has lived in both, for example, Peoria and Carbondale, as I have, there's not really a whole lot of difference in the summertime between those places. It's hot and humid in both places. It just tends to last a little bit longer in Carbondale. And so the real difference here between northern and southern Illinois climates is really in the wintertime. When in southern Illinois, it tends to stay relatively mild, although they do get more ice storms. In the northern part of the state, we can get a lot more colder air outbreaks, and those very cold temperatures can persist for quite a bit longer. So, I know that I was looking at the list of attendees here, and I know you come from somewhat diverse parts across the state, but this is just for Marion County here. What we can see is climate graphs. On the left, it's the plot of our normal temperatures. We're getting new climate normals, and I'll talk about that in a little bit in just a couple of months. And these are using the new normals. Our normals, when we could say it's drier than normal, it's wetter than normal, it's warmer than normal, et cetera, that uses a 30-year period of time that ends on the most current decade. And so in this case, our new normals are calculated 1991 to 2020, where our old ones were 1981 to 2010. So it's just a way of using more recent data. So these are showing the 1991 to 2020 averages here. Temperature on the left, rainfall or precipitation on the right. The temperature I'm showing maximum, minimum, and an average daily temperature. And you can see this is no surprise to anybody who's lived in this climate for more than just a few days. It gets warm and in some cases hot in the summertime, colder in the wintertime. We have the transition seasons where we are now between March and May in spring, and September and November in fall, where we have the pretty rapid transition from cold to warm and then back from warm to cold. Precipitation, this is what I talked about before when I talked about that climate classification. There's not really necessarily a wet season. I should be more precise. There is not a wet season in Illinois. There are wetter seasons than others, but we get abundant precipitation year round, and that's pretty much for the entire state. You can see here that, as we know, May and to a lesser extent, June and July are some of our wettest months. November, especially in southern Illinois, is another wet month when that storm track dips back down before the wintertime. And in general, January and February tend to be our driest months. That has a lot to do with the fact that air temperature is lower those months, and there's not a whole lot of humidity and liquid water in the atmosphere to precipitate out. But in general, we get an abundant amount of precipitation all year round. Okay. So that's sort of the Spark Notes version of our climate here in Illinois. And now I'm going to pivot to climate change and talk a little bit more specifically about that. Now, Earth's climates have changed since Earth has been around. In the last 4.5 billion years or so, they've changed quite a bit. What I'm going to talk about is the last 100 to 150 years of climate change on Earth. And the biggest difference is the cause. And I'll talk about that in a little bit. So what I'm showing you here, again, is kind of a different version of a schematic of Earth's energy budget. And I kind of mentioned earlier the greenhouse effect, right? Now, certain gases in our atmosphere, we call them greenhouse gases, they allow the shortwave energy from the sun to come into the Earth system. But as I mentioned, that energy is absorbed by the surface in bulk and then re-emitted as a different type of energy. So those same gases that let in the shortwave energy from the sun actually absorb, block, or trap the outgoing energy and keep it here on Earth. So the concentration of these gases, namely carbon dioxide, but also methane, which is CH4, and the vapor form of gas form of water, the concentration of those gases dictates the energy balance. So more carbon dioxide, more methane, more water vapor in our atmosphere means that we keep more energy here on Earth. And the reason these are called greenhouse gases, it's kind of an overused metaphor, is because we think about the way a greenhouse works. They have either the glass panes or the plastic wrap that allow the energy from the sun to come in, but block or absorb or trap, I should say, a good amount of the outgoing energy, which means you can maintain temperatures of 60, 70, in some cases 80 degrees Fahrenheit inside the greenhouse when outside there's not a whole lot of energy to speak of. It's kind of the same idea here where these gases are trapping that energy and allowing the temperature here on Earth to be warmer than it would without those gases. Now, carbon dioxide is the one driving the bus here. Methane and water vapor are actually much more efficient at doing this, but they're in much lower concentration than carbon dioxide. So it's really carbon dioxide that moves forward. And in fact, when we go back as far as we can go back in the paleoclimate records, going all the way back 800,000 years before the present, we see that carbon dioxide is the primary driver of temperature variability and temperature change here on Earth. And that there's no difference in that over the last 800,000 years versus the last 150. The biggest difference was the cause of that increase in carbon dioxide. So what I'm showing here are carbon dioxide concentration observations from the Mauna Loa Observatory in Hawaii. Those start back in the late 50s, go to the present. They're really held up as the primary record of observed changes in carbon dioxide. You can see here that when we started back in the late 1950s, we were at about 310 to 320 parts per million. That's the volumetric measurement of carbon dioxide. The most recent observation was in February of this year at 417 parts per million. And you can see there's season to season variability in carbon dioxide, but in general, we see a pretty significant increasing trend in our carbon dioxide concentrations here on Earth. And when we extend this back, this is showing a paleoclimate record, an actual observation from ice cores in Antarctica. The top line here is the one I want you to pay attention to. That's the red line showing carbon dioxide concentrations going all the way back 800,000 years before the present. And there's a lot of variability here. We can see some of our major glacial and interglacial cycles here from the carbon dioxide record. And certainly there were times when carbon dioxide was increasing, a lot of times when carbon dioxide was decreasing. What we see here is that carbon dioxide over this 800,000 year record was never exceeded 300 parts per million. And right now, again, we're at 417 parts per million. So we're really in uncharted territory as far as human civilization is concerned, as well as the actual change, that 100 parts per million change that we've seen just over the last 60 years dwarfs the kinds of change that we saw over the previous 800,000. So for example, we saw a similar change of 100 parts per million in carbon dioxide here over this time period, but this is over a period of about 10 to 20,000 years, where currently we've seen 100 parts per million increase in carbon dioxide over just 100 years, or excuse me, over just 60 years. So that kind of gives you an idea of how much things are changing as far as atmospheric chemistry, as far as how much carbon dioxide there is in the atmosphere. And why that is, the vast majority of it is tied to what we consider anthropogenic sources, human sources. It's really the creation of energy since the Industrial Revolution. Burning of fossil fuels, coal, natural gas, oil, and then the creation of things like concrete, for example, also has created carbon dioxide, combined with deforestation, which eliminates our ability to sequester or take a lot of carbon dioxide out of the atmosphere. That's really what's been the primary cause of our increase in carbon dioxide over the last 100 to 150 years. And so that's why I kind of pick out this part of the last 100 years of climate change in Illinois, because the primary driver is different than carbon dioxide variability over really the vast majority of Earth's history. And so, you know, we understand the physical connections between carbon dioxide and temperature pretty well. And I explained that before, where more carbon dioxide, a stronger greenhouse effect and more energy kept here on Earth, which will increase temperature. What I'm showing you here, this chart is showing 5 different data sets of global average temperature. Taking a bunch of different observations all over the globe, average them together, say what's the global average temperature on Earth, and we can see a consistent increase since about the turn of the 20th century. This is what is known as global warming. So a lot of times global warming and climate change will be used synonymously. It's actually not the right use of the term. Global warming only refers to an increase in the global average temperature that we've observed over the last 100 to 150 years. What it causes, because we're taking in more energy, keeping more energy here on the Earth system, the impacts of global warming to different regional climates is known as climate change. And so you can see here these anomalies in degrees Celsius. We're really only talking about a 1 to 1.5 degree Fahrenheit change in global average temperature over the last 100 years, which is not a whole lot when you think about the temperature change that can occur within a day at any given location. What this really is referring to, though, is the amount of energy that we're taking in, which is a lot more, and then the corresponding changes in our climate, which is what I'm going to talk about really for the rest of my talk here. Okay, so I'm going to start with changes in temperature by just summarizing how temperature has changed here in Illinois. Then I'll switch to precipitation, talk about some impacts, and then kind of like a ways forward. So just right off the bat, we're getting warmer. Air temperatures in Illinois have increased over the last 100 to 120 years. Our good observation records go back to 1895, at least at the state level. So statewide annual average temperatures increased by about a 1/10 of a degree Fahrenheit per decade. So about 1 to 1.2 degrees Fahrenheit over the last 120 years or so. I break it out. These different maps are showing warming in the different seasons. You can see that the majority of warming throughout the state has occurred in winter and in spring. We haven't seen a whole lot of warming in summer, especially in southern Illinois, and the same thing with fall. Our summers and falls have not necessarily gotten warmer overall. Minimum temperatures have increased in all seasons, but because daily maximum temperatures have not increased so much in the summertime and to a lesser extent in the fall, we don't see much of a change in the average temperature. So certainly winter and spring have warmed quite a bit. And in summer and fall, it's a little bit more of a mixed bag. We see more increases in the nighttime minimum temperatures. So, you know, what are some of the things we're seeing because of that? I know talking to master naturalists and master gardeners, one of the things that really is interesting is the longer growing season. And certainly we have seen a consistent increasing trend in growing season length. Now I'm defining growing season length here, not based on any sort of specific cultivar or, you know, when you can plant potatoes, when you can harvest them. It's more between the amount of time that elapses between the last spring freeze and the first fall freeze. And that's what I'm showing you here on the right-hand side in these maps. I talked about the 30-year normals, right? Our new normals are calculated over 1991 and 2020. And then 2 normals ago, it was calculated over the period 71 to 2000. And so just over that short time period, we can compare the average growing season length in days across Illinois, and showing these 2 maps here. And I apologize, the different color schemes here, I couldn't exactly match it here. But here in South Central Illinois, the average growing season length between 1971 and 2000 was anywhere between 185 and 190 days. All right. Now, over the last 30 years, we're looking at 200 to 210 days. So an increase of anywhere between 15 and 20 days extra. So you think about, you can chalk that on to the beginning of spring and the end of fall, an extra 10 days on either side of growing season length. And what we see in Southern Illinois is a trend of about 3 to 5 days per decade, an extension of that growing season length. And so because of those warmer temperatures, again, especially in the springtime and to a lesser extent fall, we're seeing an increase in growing season length. Now, if you're a gardener who likes to get in double crop potatoes like me, Or if you're a farmer who is worried about excess wetness in spring, maybe delaying planting, things like that, this extension of the growing season can actually be beneficial. And indeed, this is one of the few positive impacts we've seen of climate change in Illinois, is this extension of the growing season because of the warming temperatures. Now, I talked about summertime and how it's not getting warm as quickly in winter and spring. It's true, but it's also kind of a lying with numbers thing here, because summer is complicated. Summertime maximum temperatures have not increased significantly over the last 100 years, all across the state. And a part of that is because of increased humidity. So if you think about humidity makes clouds, and a cloudy summer day is going to have a lower maximum temperature, but a higher minimum temperature than a clear summer day and night. But also there are aerosols which have increased in their emissions, and those aerosols tend to block shortwave radiation, and so they can decrease maximum temperature as well. And those are really important in the summertime. But one thing we have seen in the summer, and especially in Southern Illinois, is an increase in very warm summer nights. And very warm nights in this case, I define it as nights where the minimum temperature doesn't get below 75 degrees Fahrenheit. And so we're thinking about plant physiology. We can talk about human physiology in just a little bit, but plant physiology, that it interrupts our respiration. It makes for more excessive respiration. A lot of the sugars that are collected through photosynthesis during the day can be lost because of that excessive respiration due to very, very warm nights. And so whereas we'd want that sugar to go to grain fill or fruit fill, things like that, it's actually being lost because of that. And so an increase in very warm nights does have an impact on plants, as well as humans. When the temperature doesn't get below 75 or 80 degrees at night, no matter how hot it got during the day, that's very uncomfortable. And so that can create some negative health outcomes as well. What I'm showing you here just to visualize this is the annual number of very warm nights. Again, that's nights that don't get below 75 degrees Fahrenheit in Belleville, there in St. Clair County. You can see a couple things here. If we start the record in the 1960s, there's a huge increasing trend. But in fact, over the last 30 years, we've had a frequency of warm summer nights in Belleville that's pretty similar to the 1950s. However, I'll tell you, this is a very different reason. The 1950s had a lot of very warm nights because the 1950s were very, very dry in this part of the world and extremely hot. So we had many, many days where the temperatures, the maximum temperature got 95 to 100, in some cases 110 degrees. It was during this time where we broke the all-time state maximum temperature record of 117 degrees in East St. Louis. We're not seeing that over the last 30 years. In fact, we've seen a decrease in the number of very hot days, those days where we get above 95 or 100 degrees Fahrenheit. The reason we're seeing an increase in those warm summer nights, similar to what we had in the 1950s, is because we have an increase in humidity. And I talked about that just a little bit ago, where when we increase humidity, we get more cloud cover. So what that results in is a depression of maximum temperatures. So when there's clouds, we can't reach 100 degrees Fahrenheit, plus is overall more wet conditions because of an increase of rainfall. And so we don't get those really, really, really high maximum temperatures, but minimum temperatures can't get below those critical thresholds. I'm showing that here again in Belleville, our 70-year trend in summer average dew point temperature. Dew point temperature is just the temperature that the air can reach before we hit saturation. And it gives us a good idea of a proxy for minimum temperature at night. We can see a pretty significant increase in summertime dew point temperature. So overall, we're getting the number of warm summer nights, very warm summer nights, similar to the 1950s, but not because we're seeing daytime temperatures increase, but because we're seeing humidity increase. Okay, so now looking at projections of okay, now we know what's happened into the recent past. Let's see what the models show what's in store for us into the future. Okay, these plots on the right-hand side, this is showing on the top the projections from the current out to the end of the century for the number of days where the minimum temperature doesn't get below 70 degrees, excuse me, and then below the number of days where the maximum temperature gets above 95 degrees. You can see increases are projected in both. this spread here shows a spread in the number of models, right? So we don't just run one climate model and say, this is what's going to happen. We run a good number of them. And where they diverge, we say, this is where we have uncertainty. So you can see there's a lot more spread in the maximum temperature in the summer than the minimum temperature. And what I tell folks is the models are consistently projecting warmer summers, a lot more extreme heat when we aren't seeing that in historical record. So there's a lot more uncertainty in the maximum temperature. What it does show here is that minimum temperatures and those very warm summer nights are going to continue, are likely to continue to increase into the future. The different coloring here, the red versus the green, gives us different ideas under scenarios. So we run the models under these different scenarios saying, okay, if we keep carbon dioxide emissions, because that's the primary cause here, if we keep carbon dioxide emissions at the levels that we've emitted over the last 25 to 30 years, what does that look like for the future? But let's say now we curb carbon dioxide emissions by 2030, 2040, and then go net zero by 2050. What does that create? And so what that gives us is the kind of a sensitivity of the change in climate to changes in carbon dioxide, right? And so what we see is differences between the red and the green here, showing us that the amount of change from now to the end of the century in how the frequency of very warm nights in the summertime is very sensitive to carbon dioxide emissions between now and the end of the century. And so that is really important, where fewer emissions, reduced emissions, equals overall less warming and fewer impacts. All right, so switching gears a little bit to precipitation. So we're getting warmer, we're also getting wetter. That's probably not surprising to anybody who's lived in the state for more than just a few years. This is showing annual precipitation, the plot here from the Southwest Climate Division here in Illinois. So South Central Illinois, really the southern half of Illinois, has gotten wetter at a rate of about ½ an inch per decade over the last 120 years. So 5 to 6 inches wetter than we were at the turn of the 20th century. I break down those trends here, these trends in precipitation for the two southernmost climate divisions in the state by a season here. And what we can see, this is in inches per decade. Spring, the increasing spring trend outweighs all others. So in Southern Illinois, spring, I have the summer here, my apologies. It's actually the spring trend is 2 to 4 times larger than that in other seasons. So in Northern Illinois, summer the summer wetting trend is much larger than all of the seasons. In Southern Illinois, it's really in the spring. So we're seeing that winter, summers, fall, yeah, they're getting wetter, but at a much slower rate than spring is. Unfortunately, that increase in precipitation is not coming in the form of just a few extra days of 1/10 of an inch here or 1/4 of an inch here. We're also seeing an increase in intense precipitation. So one way that, of course, when we do things like designing a stormwater drainage or capacity for stormwater storage in different subdivisions and neighborhoods, we have to think about these thresholds for precipitation. Often we think about the 100-year precipitation event, like the 100-year flooding event, right? So back in 1989, folks here at the Water Survey calculated the recurrence interval of different amounts of precipitation to tell us how intense precipitation. So if we get 5 inches of rain in a day, how frequently should we expect that to occur? And that gives engineers an idea for how to design urban and rural infrastructure. Well, because of changes in precipitation, those calculations were recalculated just a couple of years ago in 2019. And so what this does is it gives me 2 data points in time to compare how the estimated frequency of different extreme precipitation events has changed in just a 30-year period. So a couple of the most intense ones that we've seen just in the last year here in Illinois. So in January 2020 in Vandalia, they measured almost 5.6 inches of rain in just 3 days. Now, based on the data from 1989, that was a 20-year event, meaning it had a 5% chance of happening any given year, right? You think about, okay, if you're thinking about, building a house in a place where it gets flooded, you have a 5% chance of this amount of rain falling. Based off the new estimates in 2019, it is now a 20% chance, meaning the probability of this type of event occurring and the flooding that occurred along the Kaskaskia from that has quadrupled in that 30-year period. Also, a couple of other notable ones here are in Peoria. Peoria's airport measured 5.8 inches in just 6 hours. Based on the 1989 estimate, that was a 250-year event, meaning it is less than 1% chance of happening any given year. And thank goodness for that, because getting 6 inches of rain in 6 hours causes problems, especially in a river city. The new 2019 estimate, that puts it right at the 100-year event. So all the flooding that occurred last summer in Peoria and in the Tri-County area from that event, the probability of that occurring has increased by 2.5 times in just the last 30 years. One other one here, May in Chicago, they got almost 8 inches of rain in 4 days. That's where you may have seen photos from the Willis, or what I'll always remember as the Sears Tower. The basement flooding, the power got shut off to there. It's a pretty significant event. The probability of that event doubled in the last 30 years. So we're seeing more frequent, intense precipitation events because of that increase in temperature, the amount of humidity in the air that can create those events, and of course you can see the impacts related to those. All right, so projections. What is precipitation expected to be like into the future? It's much of the same, really. We see the blue colors here in the maps in winter and in spring. Winter and spring are expected to continue to get wetter all across the state. Fall to a lesser extent, and summer is really expected to maintain about the same amount of precipitation. There is some seasonality here. There is an expectation that summer precipitation will become more variable. So I mentioned Peoria's extreme precipitation last year. I like to throw out this statistic a lot because it was absolutely incredible. So the city of Peoria got over 50% of its entire summer rainfall in just that 6-hour period. So it was very dry in June in Peoria. You get 6 inches of rain in 6 hours, and then it was very dry the rest of July and into August. And so when you look at the statistics, it's like, yeah, they had a pretty normal summer, but in fact it was not, because when you get 6 inches in 6 hours, it causes flooding, and then you have drought on either side of those. And that is really the expectation for summer moving into the 21st century, is that summer precipitation overall will probably not change all that much, but it'll become much more variable. The same kind of projection plots here in Southern Illinois. This is showing total annual rainfall and the number of days with over 2 inches of rain. Same kind of thing here, where there's a lot more spread in the models than in temperature. That's because precipitation is a lot harder to model than temperature is. But overall, most models show kind of business as usual, continuation of these wetting trends that we've seen over the last 100 years or so. Okay, so I'm going to wrap things up by briefly talking about some impacts. And I've kind of alluded to some impacts, but I want to talk specifically about a few impacts to human and natural systems that arise from climate change. First one, to human health. So, as temperatures increase, it also increases the exposure risk to extreme heat. The map here on the right-hand side is showing the green dots are hospitalization rates per 100,000 people in each county in Illinois over the last 30 years. And these hospitalization rates are hospitalizations that are caused by, or the source is heat exposure. So it could be heat stroke or heat illness, something like that. What you can see is that some of the counties in South Central and far Southern Illinois have larger green dots than those more urban counties in the Metro East area, as well as in the Northeast corner of the Chicagoland area. What this is suggesting, and this is what a few studies have found, more recent studies have found, is that actually the risk of extreme heat exposure and hospitalization because of that exposure is actually larger in some of our rural areas in Southern and Western Illinois than our more urban areas. And part of that is because there's a higher proportion of the population that's doing work outside in those counties, but also because there's overall less accessibility to healthcare resources in rural counties. You may have to drive 40, 50 minutes to the nearest healthcare center, and that creates a risk. If folks are less likely to do that and more likely to only go when they have severe health impacts from that extreme heat. Another more kind of insidious health impact from climate change comes from an increased exposure to vector-borne disease. So increased temperatures, especially in the wintertime, have helped expand the range of ticks and mosquitoes and then the diseases that they bring with them. What the map here on the right-hand side is showing is from a recent survey from the U of I Vet Med School and the Medical Entomology Department here at the U of I that did a survey of different tick species and diseases all across the state. Found a couple of really interesting things. First of all, the Heartland disease, which is spread by the Lone Star tick, was confirmed in Kankakee and in Williamson counties for the first time last year. So all the way from southern Illinois up to northeastern Illinois, we see an increase in Heartland disease, which was previously, before 2019, not previously recorded in Illinois. We also have a higher prevalence of Lyme disease, of course, spread by deer tick, and West Nile, spread by mosquitoes in northeast Illinois, but also in the Metro East. And this is related to excessive wetness in the spring, followed by short dry spells in the summertime. Lastly, the Gulf Coast tick, which was before 2019 not confirmed north of Nashville. The Gulf Coast tick just last year was confirmed for the first time in Illinois in St. Clair County. It's expected that it is all across southern Illinois by this time, and that carries with it a couple of different types of diseases as well. And so as we have these increases in wintertime temperature, and as I showed you, winter is warming at a faster rate than all others, it increases the exposure risk to these vectors, the ticks and mosquitoes, and then the diseases they bring. And being naturalists, of course, we like to be outside, whether it be in our garden or hiking along some of the awesome trails that Illinois can offer. This becomes a real issue. We also see climate change impacts from extreme precipitation due to soil erosion. A new estimate, the figure on the right-hand side is showing that some maps from that study. New estimates suggest 30 to 50% of our really valuable A horizon in the Midwest has been lost since the 1800s. Part of that is extreme precipitation. Part of that is a type of agricultural management that dominated the last 100 to 150 years. That does a number of things. First and foremost, that's the livelihood of anybody who depends on the land, is that organically rich A horizon. But also when we lose that topsoil, it reduces our resilience to prolonged dry conditions. So as we talked about, if we get conditions like we had in central Illinois last year, where it was very, very wet in the spring, but then the spigot shut off when we got dry in the summertime, the amount of water you can retain in that soil really depends on the organic the concentrations of nutrients and organic compounds in that soil, in that O and that A horizon. And so as we lose that organically rich A horizon, it makes it so that water, that soil can hold on to the water for a shorter period of time, which makes it more vulnerable to prolonged drought in the summertime. And then we have what we've all heard about: higher sedimentation rates, water quality issues from nutrient runoff from agriculture and industrial sites, and just overall poor environmental quality from that increase in precipitation. Talking about forested ecosystems, there are a number of climate change impacts to forest ecosystems. I just want to hit on a couple of these so I don't go over time. One is increased disease from wetter springs. For example, oak blight is one of those that really does well when we have very, very wet, excessively wet springs, which of course we've had an increase of in southern Illinois. At the same time, when we get even just short-term drought in the state, it does put quite a bit of stress on our mesic species. That's some of our best species: red maple, sugar maple, basswood, those sorts of things. And those overall shorter but more acute droughts also favor prairie and savanna systems versus forested systems. Also, at the same time, warmer, drier conditions as we increase summertime temperatures can exceed species ecological tolerance. So we're already at the very southern edge, especially in southern Illinois, of white oak, our state tree, black cherry and shagbark hickory ranges, and that becomes a real issue as we continue to warm. But all of that being said, there are major adaptive capacity factors. So for example, oak woodlands and savannas can better adapt to our projected changes. And fragmentation by agriculture. We always talk about fragmentation on agriculture having a negative impact on the natural system. In this case, when we fragment forested areas by agriculture, it reduces gene flow. So it makes it so that invasive species can spread less easily between natural systems, as well as we don't get a homogeneous kind of a monoculture of one different type of species, which, as we know from lessons learned from ash trees, especially in urban areas. Having a monoculture in our forested areas is not the way to go when it comes to being resilient to climate. Skipping the forest to go to the aquatic ecosystems as well. You know, we see not only is air temperature increasing, but water temperature as well. That affects feeding, growth, reproduction. It can expand. Increasing water temperatures, which is what we've seen all across the state, from our very smallest ponds to our largest lakes, including Lake Michigan. It can expand the suitability for warm water fishes. But at the same time, it reduces suitability for cool or cold water fishes. My favorite fish to catch and eat is walleye, and we are losing suitable habitat for walleye, especially in our deeper lakes in southern Illinois. Warmer water plus our nutrient runoff from agricultural fields increases the risk of harmful algal bloom. You can see on the right-hand side here in lakes and streams. That is a serious issue, especially in parts of southern and central Illinois where we depend more on reservoirs for water resources. At the same time, we get pressure from invasive species. If anybody's taken a boat trip down the Illinois River anytime soon, one of these folks has probably popped into your boat, or at least gotten up pretty high. And that pressure from invasive species like Asian carp can compound on any kind of stress that's put on aquatic ecosystems from warmer temperatures and so on and so forth. So that's an issue as well. Birds are also influenced by climate change. A recent Audubon study found that 30% of Illinois' bird species are extremely vulnerable to climate change, including bobolink, red-headed woodpecker, really important species there, field sparrow, brown thrasher, wood thrush. What I liked about the Audubon study, though, is that it showed that if we reduce our warming from climate change mitigation, pretty much the reduction of carbon dioxide emissions, it would greatly reduce the overall avian risk of climate change in Illinois. And then last impact here, talking about agriculture. So I talked about the frost-free season is increased by quite a bit. That does actually help increase growing degree day accumulation. I think that really had a big role to play in 2019 when folks were planting corn into late May and early June. And amazingly, that corn made it to maturity because September was very, very warm, as we've seen September temperatures increase. However, at the same time, warmer winters increase survival and reproduction of insect pests. So it's not just ticks and mosquitoes, it's insect pests to crops as well. More frequent extreme precipitation, of course, it increases soil erosion. So I talk about environmental degradation from soil erosion. Of course, as nutrients run off, more nutrients have to be applied. So that's an economic issue as well. And then overall wetter spring plus drier summer reduces flexibility for treatment and planning. We think about some of the rules that have been imposed at the state level for things like dicamba application, which depends on wind and temperature. The increase in temperature, especially in spring, is making fewer and fewer application days. So we're just overall shorter windows for decision-making for agriculture. Okay, last thing here, what can we do? I present all of these issues. What are things we can do? And I love talking to master naturalists, master gardeners, because a lot of things that we're doing are things that we need to do. Mitigation, adaptation to reduce the impacts of climate change, it really starts from decreasing personal and systemic greenhouse gas emissions. But also thinking about sustainable urban and rural development. So green space, having accessible transportation. On the top right, this is a picture from the parking lot at the Missouri Botanical Garden there in St. Louis. You can see you break up that asphalt space with some green space, which can help water quality as well as sequestering carbon dioxide. Same thing in rural development as well. Sustainable agriculture plays a huge role. So soil and water conservation is extremely important, not just for economics for agriculture, but also for reducing the impact of climate change. And then developing local food supply and demand chains. So we don't have to have the carbon imprint of shipping all of our produce from California to here when we can grow it here ourselves. Natural resources are extremely important. Habitat restoration, especially along our major rivers here in Illinois, can really help with water and flood management. And then planning, hazard mitigation plans really help for reducing that overall change in climate risk. I have my contact information here, and I'll come back to that in just a second. One plug, and I know someone's going to talk about CoCoRaHs after me, but I want to just put in this plug really quick of why CoCoRaHs is so important. So I am the primary point person on drought and climate monitoring across the state. So a lot of the decisions as far as what parts of the state are in drought, what parts of the state are not, it falls on me. And CoCoRaHs is an extremely important decision-making tool for me. So when I look at a region to see, okay, yesterday a series of storms came through, what places got how much precipitation, we only have so many co-op stations, our long-term running stations around the state. And especially in our rural areas, we don't have very many. And the ones we do don't have a really long record. So CoCoRaHs could really help fill in those gaps. What you can see here from this map, these are active stations right now. And there may be a few missing on here, but you can see that the vast majority of Marion County and all of Fayette County, the majority of Bond County, a lot of Washington County don't have very many CoCoRaHs observers. So if you are considering, I measure precipitation anyway, I'd really like to know how much is coming into my garden. Please consider, even if you live in a relatively CoCoRaHs dense county like St. Clair or Jefferson County, we could still use more points on the map. But certainly if you're from Fayette County or Marion County, or you know somebody who lives in these areas, looking at you, Vandalia and Salem, please consider joining, because we really need data from those areas. And when I'm making the decisions of where to draw the drought lines, if I don't have data there, I can only use what I have. And so it can really be beneficial to have data points from those areas. So, okay, so I'll end there. That's my soapbox for CoCoRaHs. So thank you very much for letting me speak today. I'm really happy to take any questions. And like I have, this is my contact information here. And please, if you have any questions about anything, or you're seeing things where you live, or you need resources for CoCoRaHs or anything else, please feel free to reach out to me anytime. And just thank you again.
Thank you, Trent. I have a couple questions that have come in, and if they can continue to add. So the first one was, with the warming of winter, does that make spring and summer drier?
Yeah, we're not seeing that as much now. When we have warming in the spring, it does increase our evaporation rate, which means that soils are drying faster in the spring than they were before. But any kind of increase of evaporation that comes from warmer seasons has been outweighed by our increase in precipitation. So overall soil moisture across the state is increasing. Despite the fact that we're warmer, we're evaporating more, we're just getting so much more precipitation that it's outweighing that.
Thank you. Another question was the length of growing season. Last year had to be an exception with the 3 freezes in May.
Yes. So yeah, not sure where that question's coming in from, but here in Champaign, we had something like our 5th or 6th shortest growing season on record, and our records go back to the 1880s. So this is a good point about climate versus weather, or climate variability. Despite the fact that climate is, warming, for example, we still have variability on top of that has nothing to do with climate change. And so it's still very possible to get a late spring freeze and an early fall, or a very late or early fall freeze. And actually, because of increasing winter and spring temperatures overall, what it does is it makes the phenology, it makes plants wake up sooner. And so it actually increases the risk of having a false freeze or a false spring and having freeze damage to our tender perennials. So it's a really good point. It's a good question to bring up.
Kim had a question here. She said, you noted the clouds trapping the heat energy and mentioned extreme rainfall days. What is causing the extremes in all seasons? Is it related to the global warming? And will carbon sequestration relieve this?
Yeah, good question. So what the increase in precipitation that we're seeing overall is because warmer air can quote unquote hold more water vapor. And so when we have more water vapor, more humidity in the atmosphere, there's more water for storm systems to pull in. And so we can produce overall more precipitation, and that precipitation tends to be more intense. And that's pretty much all across the year, because every season is warming. We're seeing that intensity and that amount of precipitation change the most. Because winter is warming the most, precipitation intensity in winter is also increasing the most. You talk about carbon sequestration. that is a piece of it. Reducing carbon dioxide emissions or reducing the amount of carbon dioxide in the atmosphere is the key to reducing the impacts of climate change, including extreme precipitation. So a lot of what I talked about was reducing emissions, but carbon sequestration is pulling carbon out of the atmosphere, and that is equally important. And so yes, so more carbon sequestration, lowering the amount of carbon dioxide in the atmosphere does, the models suggest to us that does actually reduce the overall impact of extremes.
Okay. Pat had said that she's an observer for the CoCoRaHs in Terre Haute, Indiana. She's recently moved. So, and some great presentations. There's one more that came in before we show our little clip about the CoCoRaHs. Can you suggest an acceptable and brief and understandable response to any of us who encounter climate change deniers?
Yeah, that's a good question. So if it really depends on where the denial is coming from. If it's a person who you don't believe will ever accept what's happening, then you may just have to smile and move on. If it's a person who really wants to learn or engage, then what I tell people is that the climate changes. The climate has changed over very long time periods, and it continues to. What we're seeing is climate change that is a direct response of our activities. And our activities over the last 150 years we don't necessarily need to paint them as bad. They're not bad things because they've created a wonderful life, a quality of life for us. However, there is that connection. It is impacting our climate. And because there are alternatives, because we aren't just staring in the face of no solutions, because there are solutions, we really it's important for us to look to those solutions to make sure that we're as resilient as possible. So hopefully that is brief enough for you.
Thank you. So before everybody leaves, we want to show a short clip. It kind of explained what Trent kind of talked about, what information helps him. And we have a local master gardener, master naturalist. They've been trained in that. And I'm going to share my screen. And they're going to give us a brief view here of how to do this. So I'm hoping,
Hi,
can you hear it?
My name is Deanne Redfarron. My husband Greg and I are both master gardeners and master naturalists. In order to get our volunteer hours, we participate in the CoCoRaHs rain gauge monitoring program. The rain gauge is this one that I have next to me, and it is on a pole, I guess about 4 feet tall. It's important to locate your pole and your rain gauge somewhere where there are no trees around so you get a true reading. The rain gauge has 4 parts. For measuring it, okay.
Stop sharing.
Chris, the message on my screen says you cannot move a video while people are pinned.
Are pinned? Okay. Okay. Let's see. Can we? I was trying to see if I could share and then start again. Screen share. I apologize. Is it?
When I read it, the gauge inside is marked off very clearly by tenths of an inch. This
Is it,
I poured
can you
in.
see it, Gail?
It goes to about 0.69.
Yes.
On the
Okay.
gauge, it reads 10, 20, 30, 40, and so on. You just put a decimal in front of whatever your reading is, and that's what you enter in the CoCoRaHs app. So, what happens if you get more than an inch of rain? Well, obviously the small tube inside is not going to hold it. There's a groove inside, and that allows all the extra to run off into your bigger canister. Let me show you this. So here it is. I have my inch of rain in the small tube, and then it ran over into the bigger canister. So to measure this, first thing I'm going to do is remember that this is an inch, dump it out, and then I'm going to pour my remainder back into the tube and read it again. So this is 0.67. So on the CoCoRaHs app, I would enter 1.67. Do this every day. It's a very, very easy project. It's fun to track how much water and rain you've had. In the past week, we had, I think, 5.25 inches of rain in about a week's time. And if we hadn't been entering that on the app, we wouldn't have been able to look it back up and see how much rainfall we had. Thank you for listening. This is a great citizen science project. Good luck.
Try not to hit buttons. Okay, so Trent, is there anything more? And I apologize if you didn't get to see all of that video. We will send that clip out again for you. If you have questions, I know a couple had said that they actually had worked on the CoCoRaHs. Does anyone have questions or want to ask any questions of Trent before he leaves today?
I would just note that on their website, there's an enormous amount of training videos and very interesting videos, and you can view the statistics, and it's actually, if you're interested in weather, it's very entertaining. But there's to get details on how to do all that, those online videos that they have are amazing.
Does it matter if you're on vacation for a week or so and you can't record? Or will that mess up their statistics?
No, you can, so this is Trent. So they have a function where you can record multi-day accumulation. And that's what I'll do is, you go on vacation for a week, you come back, there's an inch of rain in your gauge, don't know what day it fell on. So what you do on the website is just put between March 10th and March 17th, an inch of rain fell. And that's really important because we not only look at how much rain fell on a daily basis, but over the course of a month and a year. And so in that case, it really didn't matter to us when it fell, just that's how much rain fell there.
I just entered, they asked what the CoCoRaHs site is. I entered that into the chats box for you. And as we send out, we'll be able to send out some more information. I'll send that link on how to do it and along with this website. Again, as Trent said, we kind of talked about it. That one is from Marion County. That kind of gave us a little short clip. They do that and they're right on the border of Jefferson, Marion County. He is looking for more observers and they were even interested, Trent, in giving you more data about droughts and local things that are going on throughout the year. Do you want any of those type of information from any of the other observers that are going?
Absolutely, yes. If you are a CoCoRaHs observer or you want to become one, through the same system, you can do condition monitoring reports. And what those are, it's through the same website and everything. They're actually probably easier to do because you really only have to do them maybe once a week or once every couple weeks. They let you put in whether your conditions where you live are severely dry, moderately dry, severely wet, moderately wet, normal. And for folks who are master naturalists, master gardeners, they know where they live. They've lived there for a while. You know what severely dry looks like versus mildly dry. It can be really helpful. And then you can put notes to say my local stock pond is below normal. My soil, I dug down to 4 inches and it was bone dry, or I got puddling in parts of the yard that I never had puddling in before. That's extremely helpful for me because again, even if I have rainfall data and it looks like things are wet, but in fact, people on the ground are telling me, nah, it's actually pretty dry. That really helps. And so if you are doing CoCoRaHs, I really encourage you to just put in a condition report, maybe again, once a week, once every couple of weeks. And if you're not doing CoCoRaHs, but you still want to report what's going on around you, feel free to email me and say, hey, it's really dry here, it's really wet here, things like that. I'm always happy to hear from folks on the ground what things are going on.
Can you buy replacement parts? They did some construction at one of the offices and took the 4x4 post out and it had my bracket. Can you just get a bracket somewhere?
Yes, I actually had to do that myself the other day. So there's the main website that you go to for ordering. Let me see if I can pull it up, but you can, on that website, you can actually just order the inside gauge, the outside gauge, or the bracket. And it's cheaper than, okay, here.
I can look that up.
That's okay. I got it here. I can just put it. It's Weather Your Way, and that may take you to the full gauge. But if you mess around on the website, they'll have just the bracket, and I think it's like $10 instead of $35 or whatever it is.
Okay. Thank you for that.
Okay, is there any other questions? Trent, also, will you be sending out your presentation that we can include to anybody that needs it?
Yeah, absolutely. I'll send that to you now.
Okay.
And yeah, feel free to distribute as you want.
Okay, well, thank you so much. And we appreciate everybody taking their time out today to attend. And again, Trent, thank you for joining us on giving us a presentation and answering all of our questions today.
Yeah, thank you so much. If there's any other follow-up, please feel free to email me. Take care then.
Thank you.
Bye.